In today's video, we're going to look at the different types of elasticity, explain the terms spring constant and Hooke's law, and finally look at some force extension graphs. When you apply a force to an object, you could cause it to compress, to stretch, or to bend. This is easiest to see with a spring, but the same concept applies to other objects too, like a ball or a phone. These objects are just less elastic, so it's harder to notice any kind of change in shape. Whatever the object is though, we always have to apply more than one force if we want it to stay still. Otherwise, the object will just move as we pull or push it. Even if you squish something against a floor, and so you only apply one force, the floor itself is applying a force upwards, so there are still two forces acting on the object. Now, when an object changes shape, we say that it's been deformed. But importantly, there are two different types of deformation that you need to know: elastic and inelastic. If an object returns back to its original shape after the forces have been removed, then we call it elastic deformation, because it's able to spring back like an elastic band. However, if the object doesn't quite return to its normal shape, and stays deformed in some way, then we call it inelastic deformation, or sometimes plastic deformation, because it keeps its shape like plastic. The next concept we need to look at is extension, which is the increase in length of a spring when it's stretched. For example, if we hang a spring from a solid support, then we can measure how the spring's length changes as we add downwards force to the bottom of the spring. Now, even before we've had any chance to add force ourselves, the spring's own mass will be exerting a force downwards in the form of weight. And this means that the natural length will be a bit shorter than the spring itself, because there will already be some extension. This extra length is generally pretty small though, so we tend to ignore it and think of the entire length as the natural length. If we then add a mass to the bottom of the spring, the weight of that mass will pull on the spring and so increase its length, which we can then measure as the extension. One thing to point out here is that the solid support will also be exerting an equal but opposite force upwards. And this is why the spring doesn't fall down when we add any mass. It's being perfectly balanced by the support. As we increase the force on the spring, for example, we add more mass, the extension increases proportionally, which we can write as F is proportional to E, because F is the force and E is a symbol for extension, although you might sometimes see it represented as an X instead. Exactly how much the spring extends, though, for a given force, depends on the particular object's spring constant, which is denoted by the letter K. And if we add this into our force extension equation that we wrote in the bottom left, we get F equals KE, with K being measured in newtons per meter and extension in meters. The spring constant tells us how many newtons it would take to stretch the particular object, like this spring, by 1 meter. So the higher the spring constant, the stiffer the material, because it requires more force to stretch it. We can show this relationship by plotting a graph of force against extension. As the force increases, so does the extension. And because it's a straight line that passes through the origin, we can tell that force and extension are directly proportional. We call this relationship Hooke's law. And importantly, all of this deformation will be elastic deformation, meaning that once the force is removed, the object will return to its original shape. There is a limit to this relationship though. At some point, our line will start to curve, and we call this point the elastic limit, or the limit of proportionality. After this point, Hooke's law no longer applies, and the object won't necessarily go back to its original shape, meaning that it will have been inelastically deformed. Anyway, that's everything for this video, so hope you found it useful, and we'll see you soon.